we'll get started, right? So, the objective today is to make a slightly faster program than what we had written yesterday, using the same concepts what we had seen for the transmission lines when we used vector updates. We are going to do the first the vector updates first, and then we are going to see some use cases. We are going to put some interface, we are going to put some multiple interfaces. We are going to plot, we are plotting only the electric field. We are also going to see how Hx, Hz look like. We have also updated them. So, there are a variety of things that we will be changing in the code once we have a fully working code that is reasonably fast. Okay. So, I will go ahead, open a new program. I have this program here for reference, right. The initialization section will remain the same, all right. Nevertheless, I will go ahead and type it, right. Okay. So, I will use the same dimensions of the space, 100 by 100 space units. Okay. So, yesterday some people were confused about y dim, all right. It is just y axis of this monitor, all right. But just to clarify that confusion, I will also use x dim, right. I mean, I will use z dim, so that confusion is gone. We are plotting the xz plane, right. The total time for which we will run the simulation, we will keep adjusting this as we go forward. Initially, I will keep it at 10. The reason is I want to check whether the program works correctly. After that, I will increase the amount of time, right. And I will have the same variables for x source. So, I will be having a point source at the center of the space, right. Yesterday, I had used y dim, right. Now, I am just using z dim so that you do not have that confusion going between x y axis of this monitor and the program. One more aspect that we had seen yesterday was right, the calculation of delta t had some nuance associated with it. We had used something known as a current stability factor. We did not go into a lot of details because that is an advanced topic, but for the 2D case you have to take care of this number, all right, and the number here is 1 by square root 2, all right, the case of vacuum. So, we will just keep that number in the code. Remember, the objective of these lectures is not to go deep into the computational aspects of electromagnetics at all. It is just to give you a working example to start with, so that at the end of the course you have a set of programs using which you will be able to manipulate things and go on. Also, it will form a strong base for the advanced level courses, all right, where you will have the basic skeleton. Then you can go deeper into each and every aspect of the code and start learning more from that, right. So, once again we are using relative units. So, what we are trying to do here is we are setting the permittivity and permeability of vacuum to 1, just like yesterday, which means that the velocity in free space or vacuum will be considered as 1, and everything else will be considered with respect to the velocity in air. This is done so that you do not have approximation errors while doing some updates, because it is a very tiny number, all right. You do not have any 0 errors coming into the picture. Similarly, mu 0 is equal to 1. Consequently, velocity becomes equal to 1 in vacuum at least, right. Okay. Space step in both x and z direction is set to 1. The only thing that remains is calculation of delta t. Okay. So, that is s times this is the only change that we had made, right. Delta t calculation had to be taken into it has to take into account the distance traveled by the wave in the diagonal direction in a 2D grid, all right. So, the distance is multiplied s times delta divided by c, okay. Now we just need to initialize some variables hx, hz, ey. Hx we start with all zeros. Okay, we are just using xdim comma zdim. If you did happen to use the same initialization as yesterday, you have to continue with the same variable names. There are no problems with it at all. Hz, same electric field y direction. So we are considering perpendicular polarization. So another thing that we want to do today, for which we didn't have enough time in the last lecture, is want to change permittivity in different regions, and we want to closely analyze what is happening, at least visually. We know that when we have a single interface, we are going to experience some reflection. The reflection is going to have a reflection coefficient that is angle dependent, because you had cos theta t, cos theta I coming into the picture for the reflection coefficients. You also had a transmission coefficient that was also angle dependent, all right. So we would like to be able to see, if not everything, at least for the normal incidence case, what does the visual picture look like when you have waves traveling forward and then hitting the interface, coming backward. What happens to the region in between? We need to see a few of these aspects, and then we have to see if by using this program I can open up a new topic for discussion in the following weeks. Okay. So I want to be able to have the freedom to change epsilon at different places. So epsilon has to be a matrix whose dimension is xdim comma zdim in this space. So I will be able to address epsilon at each and every point, right. So I'm going to have epsilon 0 multiplied with ones of xdim comma zdim. So as of now, the epsilon matrix will have all ones at all the spaces. Later on, I would change the epsilon at specific coordinates. Okay. Similarly, I'll be having mu to be mu naught times ones of xdim comma zdim. Okay. Now the initialization part is over. This is identical to the code that we had yesterday, except that instead of ydim, I am just using zdim so that people don't get confused at all. Still in the xz plane. Okay. Now we had a giant time loop, so I'll write a for loop, right, n equal to 1 to time total. So for all instance of time, I want to make use of the difference form of the Maxwell's equations for this particular polarization configuration, and I want to create some updates for the electric field and the magnetic field, right. So yesterday we had used two for loops. One for loop was going for the magnetic field calculation, another for loop for the electric field calculation. This is simply because for the magnetic field calculation we had used so we had used forward difference for the spatial derivative of electric field, right. So the limits are different when you take forward difference. So you have to go from 1 to xdim minus 1, 1 to ydim minus 1. Whereas when you were calculating the electric field update, we were using backward difference for the magnetic field. So we needed to have two for loops, all right. And what we are doing today is we are still sticking to that, all right. But the objective is to remove these for loops and use vector updates, all right. Okay. We are still going to continue to use forward and backward differences, but we are just doing it by vector updates. Okay. So all I want to do is remove for loops, all right, and I want to incorporate this I equal to 1 to xdim minus 1, j equal to 1 to xdim minus 1, etc. into these parts over here, all right, wherever I have array indices, and remove the for loops. Internally, Octave will take care of calculating them by distributing them in a better, more efficient way than a for loop, which is a serial calculation, right. So we go back to the program. Okay. So I look at the first line what I had yesterday. I had hx of I comma j, right. So I had hx of I comma j is equal to hx of I comma j, right. But this I and j were being defined in the loop, all right. So, I varied from 1 to x dim minus 1, j varied from 1 to x dim minus 1. So, all I need to do in my code now is I need to stop using I and j and directly use the definition of I and j from the for loop. So, I will just go ahead and replace I with 1 colon x dim minus 1 and replace j with 1 colon z dim minus 1, right. Again 1 colon x dim minus 1 and j will look like 1 colon z dim minus 1. So, all we are doing is from the previous program, we are removing the for loops and the definition of I and j, right. We are going to plug it in directly into the update itself. So, suppose I have I comma j, I will be replaced with 1 colon x dim minus 1, j will be replaced with 1 colon z dim minus 1. Suppose I had I plus 1, it means that you will take the lower limit, which is 1, add 1 to it, it will become 2, and the upper limit x dim minus 1, you will add 1 to it, it becomes x dim, all right. So, wherever you have I plus 1, you will substitute for the lower and upper limit, do the algebraic operation and then put them back in the code, all right. So, there is no big change over here, but we will go over it systematically at least for the first update over here, right. So, I have plus delta t okay. Okay. Now, compared to the program yesterday we had delta t divided by delta times mu of I comma j. Okay. Remember that when we are executing something inside this for loop, this delta t is a single number according to our definition. Delta is a single number, so it is 1 for delta, all right, and it will be s multiplied by delta divided by c. S was 1 over root 2. So, it is a single number which will be substituted here. Mu of I comma j is a single number. Okay. Now, since we are doing this slightly differently now because we do not have a loop, we want to be explicit by using this dot operator in front of division multiplication. Just means that whenever you are going to, mu is now going to be a matrix. Mu of I comma j will be like mu going from 1 colon x dim minus 1 comma 1 colon z dim minus 1. You have to pick up specific elements and multiply it at that instant of time. So, in order to tell that we are going to be using an array, it is better to use dot slash. It just means that every element of the array will be multiplied with this number, all right. It will not attempt to perform matrix multiplication or matrix division. Remember, matrix multiplication would be like you take a row and multiply with the column of the second matrix and then you fill up the first element. We do not want to do that, okay. So, in order to say that take the corresponding elements and multiply them, or take the corresponding elements and divide them, you can use the dot operator, right. So, I want to be clear, so I just use the dot slash. So far delta t is a number, delta is also a number, but mu is going to be a matrix, and according to the program I had, it was mu of I comma j, right. So, I is replaced with 1 colon x dim minus 1, j is replaced with 1 colon z dim minus 1. So, I will close this entire term and then it was multiplied with the derivative of e, right. Just go backward and I will keep this part here. So, I had e y I comma j plus 1 minus e y I comma j. So, all I need to do is I need to use the same thing. Instead of I will use 1 comma x dim minus 1, j plus 1 will look like 2 comma z dim, right. So, I need to substitute for again e y of I comma j. So, I will go ahead e y of I comma j plus 1 becomes 1 colon x dim minus 1 comma 2 colon x dim I comma j plus 1, okay. So, 2 colon x dim minus e y 2 colon z dim. I think I made a mistake. Good. Okay. Towards the end, I place a semicolon. I'll just wait for everybody to catch up with the code. Okay. So, now I will proceed for Hz, okay, which is in the same loop, right. So, I will go ahead for the next line and I will insert a new line for Hz. So, if I look, I have Hz of I comma j is equal to Hz of I comma j minus something. So, I will go systematically. Hz of I comma j looks like 1 colon x dim minus 1 comma 1 colon z dim minus 1 is equal to Hz of I comma j plus some update term. So, it is minus delta t divided by delta. So, what I will do here is I will just copy from the previous line, okay, this coefficient, okay. I will just copy from the previous line because it is identical, okay, this part is identical, all right, and I need to have I plus 1 comma j for the electric field minus E y of I comma j. So, all I am going to do is go back to the program. Once again, I am just going to copy paste from the previous line and then manipulate it. So, I had I plus 1 comma j. So, I plus 1 will make it 2 to x dim and 1 comma z 1 colon z dim minus 1 for z and the last term is anyway E y of I comma j. So, it remains the same. Okay. Now, we had another for loop for calculating the electric fields in the prior lecture. We are going to remove that. The extents of the loop was going from 2 to x dim and 2 to y dim, all right. Now, all we have to do is replace I and j with 2 to x dim and 2 to y dim. So, we will have another line for E y. So, I will just take E y of I comma j plus something till here. I will copy it, I will paste it, start replacing things. Okay. So, I have I comma j, but I comma j now the definition is 2 to x dim, 2 to y dim, all right. So, it is different from the previous loop. So, we have to be a little careful. So, I is looking like 2 to x dim. So, I will put that as j is 2 to z dim, right, is equal to E y of 2 colon x dim. Plus I have some coefficient for the derivative of the magnetic field. So, previously I had delta t divided by delta times mu of I comma j. Now, I have a similar form. I just have delta t divided by delta looking identical to the prior updates. Instead of mu, I am having epsilon of I comma j, all right, that is all. So, I can go back to my program. From the previous lines, I could copy this coefficient paste it in the current line and make some adjustments. Okay. So, I had instead of mu I had epsilon and instead of I comma j previously I comma j was 1 colon x dim minus 1, so I have to make it 2 to x dim, and I had to make it 2 to z dim. All right, these are some two changes that you will have to make. One is you will have to change your mu to epsilon, and the other one is changing I comma j definition. All right. Once you have this, then the remaining part we will have to fix. It's going to be a long equation, but all right. So I have hx of I comma j. Right. So I'll start with this. Two colon x dim, I comma j will make it 2 colon z dim. Minus hx of I comma j minus 1. So, I am just going to take this part, put a minus sign, and hx of I comma j minus 1 will make it 1 colon z dim minus 1. Okay. Just then I have hz of I comma j. So, it is minus hz I comma j. Just copy this part. So, instead of I, once again I put 2 colon x dim. Instead of j, I put 2 colon x dim. Yeah, that's it. And the last term is some plus hz I minus 1 j. So, I will just use, instead of I minus 1, I will have 1 colon x dim minus 1, and j will look like 2 colon z dim. Just check where the bracket closes. Okay. All right. So, now we have finished creating the updates for all the quantities. All we need to do is set a source and make some plot commands. Okay. So, we will set a source at x source comma y source as we wish. Right. So, I will be having ey at x source comma z source is equal to 1. So, right at the middle you will be having a source being set to 1, and then some plots. Okay. So, I am just going to I will just do image SC of EY, color map will be jet, and I want the color bar to be present. EY what? EY it is 4 delta plus 2. Ooh. Okay, good. Okay, I'll also give it a title, just like in the previous class, right? Num to str of n. So I just want to know which time step it is showing me the plot for, and then as usual we'll have a pause command so that we can see the plot. Okay. Okay. So, now we are done, and now you can see that the code looks a little bit more simpler. You can clearly understand that there are 3 lines for doing essentially the curl equation update. The remaining are just definition of quantities, plot commands, etc. Right. So it's a much cleaner code. Let's try to run it and see whether we are getting something. Right. Something is not all right. Right. So I'm having an error somewhere. Okay. So okay, I think I understood what's going on. There is a tiny error that can be easily fixed. All right. I think when we are dealing with mu and epsilon doing this inside this, and then we are multiplying it with Ey, all right, and then Hx, we have to be a little careful. I think we have to say that it has to be an element wise multiplication again, all right. So just the error is very tiny, it can be fixed. In the first line update for Hx, after the delta t by delta mu calculation, instead of this multiplication sign, just put a dot in front of it. It's attempting to do matrix multiplication there, right. Same way in the second line of code, place a dot here. Third line of code, place a dot here. I think that's the error. It's attempting to do matrix multiplication there, whereas we need individual element wise multiplication. Okay. Just go ahead and run this now. All right, there we go. Okay. So now I have a code that runs, right. Now I would like to just get a feeling for the code that we had before and the code that we have now. So I'm just going to take the prior code and make the time total equal to say 20, okay. And I'm going to keep x source as x dim by 2, y dim by 2, etc. I'm going to be having a similar source. I will not give any additional parameter, okay, 0, 0, 0, 1, okay. So I have identical codes. All I just want to do is I want to just get a feeling for the amount of time it takes to do all this, all right. So I'll put a tick command here, and at the end of the code, I want to have a talk, right. So I'll go ahead and run this code first. This is just for our information. Okay, it's about 17 seconds, okay, with the for loops. Let's just have a look at what is happening with this. So I had, take a talk, and I think the number of time steps was 20. So hardly 3.5 seconds. So you get a tremendous update speed over here. So it is, that's why we spent this much time, because it's a 6 times speed up just by changing the loops, all right. This makes it a little bit more convenient for the stuff we are going to try in the class, right. So the first thing that we can do is now start to put a source which is slightly different. Right? Yesterday we had talked about how to make a plane wave source. Now we are having a circular wave front that is going all the way. So yesterday one of the things that we were doing is we were using this x source minus 25 to x source plus 25. Okay. If I make this change over here, I'll have a bunch of points. Okay. I'll have a bunch of points acting as a source. No longer is a point source. Right. I'm going to run this code again. Now I can create some wavefront that looks flat, at least in these directions. You cannot prevent the electromagnetic field from doing this. It's normal for it to do this because there's nothing restricting it from going in a collimated manner at all, all right. So you're creating some wavefronts over here which looks flat, all right. So you could always try to play with this, right. One of the things that we can start doing now is starting to put some different material interfaces. So what I'll do is just before the for loop, okay, I'll just make epsilon, right, in some positions to be 4, all right. Currently epsilon is 1, in some other positions I would like to make the epsilon 4 times, so that 1 by square root epsilon mu in those times becomes half, all right. So, you will have half the velocity, right, and we will see the consequences of what is happening there. So, I will just make it, so let us say that I have, way I have plotted, let us see, x dim by 2 colon x dim comma colon. Okay. So, all I have done here is epsilon for x values going from x dim by 2 to x dim for all values of z is going to be equal to 4. Right. It will take some time to visualize what exactly we have written over here. So, what I will do here is, for you to visualize what has happened, I will just pause briefly and then I will maybe show the plot for epsilon itself. So, I will just do an image SC of epsilon and pause maybe I do not know the unit of pause command, so I am assuming it is seconds, but we will try and see, right. Okay, so that is how it looks, right. So, go for it, I will do it once again, right. So, the way we have plotted epsilon, it looks like this. We wanted it the other way around, because now we are having a source that is going in both of them, but that is fine, we are getting a comparison anyway, right. The other thing that would have been useful here is having a color bar, so I know what is what, right, and maybe increase the pause to 5 so that I can read what is in the color bar. Okay. So, yellow is 4, right, the black region is 1. So, I can quickly notice that in the bottom half the velocity is smaller as expected, all right, and one could also take a look and see whether it is approximately half, right. You can always do that comparison and see. Okay. So, I can see that the velocity is different. Now, at this stage what I would like to do is I would like to change the source a little bit to not be just like 1, and I would like to change it to a sinusoidal source of some n by 4, okay, and I would like to allow it to run for a longer amount of total time. So, total time just making it 100. Okay. So, all I have done now is I have changed the source to sine of n divided by 4, and the time total I have made it 100 because I want to see for a longer amount of time what is happening. So, I am just running this, right. Okay. Previously when I had a constant E source, I noticed that the velocity of travel was smaller, but now I am also seeing that the wavelength in one medium is much smaller than the wavelength in the other medium. So, the effect of permittivity variation is two things. One, it affects your velocity, and the other one, it affects your wavelength, all right. So, higher the permittivity, smaller is going to be the wavelength, lower is going to be the velocity of travel. Okay. So, this is the conclusion that one could make, right. However, in the course we had seen slightly different scenario. So, I will just push the source to some one side, because having a source right in the middle is good for the program, but when we had seen something in the class, we had source on one side and we had an interface on the other side, etc. So, what I will do is I will make it look slightly different. Okay, I will go to the definition of epsilon where we had modified it. Okay. So, I will just change it to the other orientation, so that visually it is easier for us to see what is going on, right. So, I just made epsilon of colon comma z dim by 2 to z dim. So, I just rotated the permittivity profile 90 degrees. Okay. So, this is good. Now, we have the source being placed as a line exactly on the interface, all right. So, we are having some amount of electric field going this way, some amount of electric field going this way, and it is clear that on the left hand side it already reached the left side boundary, it is getting reflected from there and it is forming some patterns, all right. These patterns are interference patterns that are happening because you have a forward wave that was going and hitting the interface, and because of the reflection coefficient being 1, it's getting reflected and you're having some interference. So, the concept is very similar to that of your transmission line. You had a forward, you had a backward wave. Only thing is the visualization part. Previously we had graph like visualization parts because you were taking one line along this horizontal part and then you are visualizing it in transmission lines. Now you are doing it in 2 dimensions and it's a little bit tougher to do this mentally, but at least now you have something to see, right. Now we have concentrated on Ey. For the sake of completeness, why don't we have a look at the other quantities that we have spent time in writing the update equations, Hx and Hz, right. So, first I will just make this image SC of Hx, right. Let us observe what is happening. This is what Hx seems to look like. If you are careful, you can go back and make some different analysis. You can see the amount of Ey on one side, amount of Ey on the other side, and see is Hx lower on one side compared to the other side. Is the magnitude of Hx different in different sides? Why is it so? You could make all that analysis. But this is what Hx seems to look like, right. If I want to take now Hz, looks completely different, right. Normally, just by looking at the Maxwell's equations, it would not have been possible for you to visualize that Hz would look like this, right. So, generally it is very tough to visualize these equations unless you write a program and actually start drawing inferences. And the other thing that we also want to stress is, it is not enough if you give a plot of one quantity, say electric field alone, because if you see the magnetic field, another component, it looks very different, and many students will find this also non-intuitive. Why is this happening? But this is exactly the solution to the Maxwell's equation. We have not done anything at all. We just put a source and allowed the equations to solve for the fields at different points at different times. But this is what it looks like, but I do not think anybody would have visualized that this is how the magnetic fields would have looked like. So, there are 2 things. Whenever you are sharing your results with other people, it will make a lot of sense to give them all components, whatever you are, if you are dealing with perpendicular polarization, you have to deal with Ey, Hx, Hz, so that the person gets a clear idea of what you are talking about. Also, Ey and Hx looked similar, they are not the same, they looked similar, alright, but Hz looks very different, alright. So, we have to look at all these quantities and then only make some analysis, right. So, this is one thing, right. Now, we will extend this program a little bit more. I will move the source a little bit to the left side, right. So, I will just make it X source, right, looking like 1 or 2, right. Z source can be the same. I just want to see what happens. Oh, maybe I had a array out of bounds error. Maybe I will just make Z source. Z source is equal to 2. Okay, because right now I do not have an idea which is X, which is Z, so I will figure it out as I go forward. Right. just run it. I'll just figure it out as I go. Okay, again we are plotting. It's in the correct place where I want. It's not the quantity that I want to plot. So I'll go ahead. So I'll plot EY. Okay, so now I have created some decent looking plane wave fronts. They are traveling from the vacuum. They are hitting an interface. Some portion of it is getting reflected. I think I should have run it for longer amounts of time, so I'll just make this time total to be 200. Okay. So I'm having a plane wave coming from the left side, right, hits the interface, creates an interference pattern or a standing wave pattern on the left side. A portion of it is transmitted to the right side. So we know that the consequence of going to a denser medium is having smaller wavelength in the medium, and the speed of travel is also going to be lesser in the second medium. But you can always see on the left side, all right, it looks very messy because of the interference patterns that you have. So this is a good starting point, all right. In order to visualize very cleanly, it may be a good idea to kill some reflections happening from the boundaries. See, all this happened because you had the wave going from the interface, going and hitting the left hand side boundary, all right, and then bouncing back, right. Suppose we found a way to kill any wave that goes from here, right, to the interface to not come back, then this would look like a cleaner way, all right. So manipulation of boundaries is very important. So in the case of transmission lines, we had made use of what's known as absorbing boundary conditions. One could extend the same concept there. So people use these conditions just to have a cleaner visualization without multiple interferences in the first medium, right. So you could have absorbing boundary conditions over here. We will look at that a little later because now it's an overkill, right. Now you have normal incidence, all right. If you were to look at what is the transmission reflection coefficient in a clean simulation, you will be able to find out it's n1 minus n2 by n1 plus n2, or no, eta 1 minus eta 2 by eta 1 plus eta 2 is the formula that we had. You should be able to verify that at least with this program. In order to create plane waves going at an angle, all you need to do is define a source at different xy coordinates equal to some sine something. So how normally people do it is they will create a set of xy coordinates. So they will just say that, okay, I want a line at 45 degrees to act as a source. So you'll just say y equal to mx plus c. M is going to be equal to 1 for 45 degrees. Constant is just depending on where you want to place the source, along the vertical direction. So you can always start at 0, doesn't matter. And then you will calculate x is equal to, say, going from 1 to 25, y will be equal to m times x, right. You will create one vector over there, then you will take ey at these positions x comma y is equal to 1. Then you can create some slanted source, you can control the angle, all that, right. So you can do that, you will be able to observe total internal reflection, etc. all right. But the only problem here is I am having 100 by 100 spatial steps. When you start putting tilted sources, you also have to take into account that your simulation area should be large enough so that the plane wave has enough space to go and actually hit the interface, right. The way we are set up, if we keep a source at the bottom, it may actually just reach the edge of the interface at the end of the simulation. So you need to create larger. I will leave that to you over a period of time. You will get confidence and you will be able to do these manipulations. But what else can we do with this which can lead to more interesting things in the later classes? Okay. Now we have two materials, two different refractive indices, right, and we have already talked about reflections. We also talked about total internal reflection. What if I created a medium which is, say, higher permittivity in the middle, lower permittivity on the top and in the bottom? That is, I will have air in the top, air in the bottom, and I will have a layer of material with permittivity equal to 4 in the middle, alright. So, we are just making a little bit slightly different configuration. So, what I am going to do now is I am going to change my epsilon to look like that. Okay. So, currently I had left half, right half, etc. So, I am just going to make it, just going to or I will just make it even smaller, x source minus 1 to x source plus 1, make this equivalent. Let me just reduce the amount of time because I want to see the permittivity profile that I am doing. I will just make it 2 time steps. Right. This is what I am doing now. I just want to verify, okay, alright. So, I have a horizontal stripe of permittivity 4, alright, and I have a large source there. I want to create a slightly smaller source. Why don't I make the source to not go so big, alright. So, I am having x source minus 25 to x source plus 25. I will just make it x source minus 1 to x source plus 1, right. That is all. I think I have a decent program to begin with. I will just start with 20 time steps to check if everything is okay. Okay, seems okay. So, I will go ahead and run this for a longer amount of time, make it 200 and then let us see what happens. So, we are able to observe that when we had a simple profile with a point source, alright, we had vacuum everywhere and a point source, it was giving out circular wavefronts and the wavefronts were spreading everywhere in the spatial domain. Now, I placed a strip of higher permittivity in between the vacuum and I launched an electromagnetic wave on one side. I am seeing that most of the electric field is actually within that stripe. Okay. I guess now you know where we are going to go for the next classes, right. We are going to talk about waveguides, alright. So, we are talking about, this is the simplest form of modeling a waveguide. So, you are having a glass waveguide, you can say that permittivity is 4. It is a piece of glass placed in vacuum and you launched a source and it turned out to be a guided wave medium, alright. So, it takes it, you can also make it look like arbitrary shapes using a program, you can modify epsilon in the way you want, alright, and you can start creating patterns and observing what is happening, right. So, but that is the general direction. However, there is a detail. Here we are talking about a specific kind of waveguide called dielectric waveguide. That is, you are having a dielectric region surrounded by 2 dielectrics, but we are going to learn about the extreme case. We are going to talk about metal dielectric interfaces, alright, first, because we will talk about parallel plate waveguide, rectangular waveguides first to understand. Dielectric waveguides we will see towards the end of the lectures, or if we run out of time, then you can also read it on your own. But from the point of view of simulation, this is the simplest way of doing it, right. So, you can imagine this region to be core of a fiber and the outer region to be just vacuum, right. You can also replace the index of the outside region to be slightly lower and see what happens, right. You can create any profile of permittivity and observe. So, now you have a tool, alright, all you need to do is go back and manipulate and play and see what you can do with it, okay. So, I will stop here, we will meet in the next class.